Hello, everyone. So last time we looked at the probability preliminaries and the basic probability theory that we need in this course. And also on lecture 2, if you remember, so we saw that lecture 2, that if you remember, if there exists, if for number for integer n, for an integer n, Kn has the property that it has a red-blue coloring that contains no monochromatic Kr, then we can say capital R of R and R is bigger than n. Okay, so to explain this, think about capital R of 3 and 3, which is bigger than 5. Remember, capital R of 3 and 3 was 6. And why was it 6? Why it was not 5? If you remember, so we considered K5, so n was equal to 5. And we said, okay, there exists a red-blue coloring of K5 that contains no red triangle and no blue triangle. So once we constructed a red-blue coloring of K5 that contained no red triangle and no blue triangle, meaning no monochromatic K3, we could conclude that capital R of 3 and 3 has to be bigger than 5. So similarly, if let's say you have an integer n that Kn, there exists a red-blue coloring of Kn that has no monochromatic Kr, we can conclude that capital R of R and R has to be bigger than n. Okay. And by the way, so this one, I can say convention as such coloring of Kn. So what do I mean by such coloring of Kn? I mean that contains no monochromatic Kr is called a good coloring of Kn. Because it's hard to repeat this sentence every time that, we have an integer n such that Kn has a red-blue coloring that contains no monochromatic Kr, just a good coloring of Kn. Okay, and we are not judging whether it's really good or not, it's just a convention. Because you can say it's not good because it shows that capital R is a bigger number if you prefer Ramsey number to be a smaller number. Okay, now let's get into the main topic of today, which is deriving lower bounds for capital R of, let's say, K and K for the Ramsey number. So we already saw that upper bound for Ramsey number is exponential. We'll see today that the lower bound is also exponential. Okay, so let's start with a theorem which is proved by Erdos in 1947. let n and k bigger than or equal to 1 be integers such that n choose k times 2 to the power 1 minus k choose 2 is less than 1, then we can say that capital R of k and k is bigger than n. Okay, so this is a lower bound for Ramsey number R of k and k. Now, and how can we check whether this bound holds or not? There's just one condition that we need to check. So once you give me two numbers n and k, I'll just immediately check whether n choose k times 2 to the power 1 minus k choose 2, as you can see here, is less than 1 or no. If it's less than 1, I can immediately say that capital R of k and k is bigger than n. Now the question is, the first question before proving this is this bound sharp? Meaning that if, let's say, this expression is not less than 1, then what happens? Can we say that, is it possible that capital R of k and k is still bigger than n, even if this expression is not less than 1? The answer is yes, it's possible. So this bound is not sharp. Okay, let's look at an example note. Okay, the way that I'm going to, it's very simple to check that this bound is not sharp. I'm going to check it with k equals 3, because we already know capital R of 3 and 3 is 6, right? So this is a very simple example. You know, I always say in all courses that I teach that whenever you want to learn a concept or theorem, first verify it or check it for the simplest example that you have in your mind. In Ramsey theory, you know, the simplest example, capital R of 3 and 3 is 6. We already proved it in the beginning of this topic. So note the bound obtained by this theorem is not sharp. Because see, if I said k equals 3 and let's say n equals 5, well, we know that capital R of 3 and 3 is bigger than 5. But if I check, I can easily check that, you know, 5 choose 3 times 2 to the power 1 minus 3 choose 2 is not less than 1. Similarly, k equals 3, n equals 4. Again, you can check that this one is not 4 choose 3 times 2 to the power 1 minus 3 choose 2. Again, it's not less than 1. And k equals 3, n equals 3. Well, this one, yes, we can check that. 3 choose 3, 2 to the power 1 minus 3 choose 2 is less than 1. So that means capital R of 3 and 3 is bigger than 3. If you want to use this theorem, we can conclude that capital R of 3 and 3 is bigger than 3. But we know that capital R of 3 and 3 is bigger than 4 and bigger than 5 as well. But we cannot conclude those using this theorem, meaning that the bound given by this theorem is not sharp in this sense. Okay, now let's try to prove the theorem. Proof of theorem. Okay, so I'm going to consider a random red-blue coloring of Kn. Okay, so remember n and k are fixed and given to us. So I'm going to consider random red-blue coloring of Kn. Okay, so if you remember the remark that we just said above, so in order to show that capital R of k and k is bigger than n, it's enough to show that Kn has a good coloring. So good coloring means a red-blue coloring that has no monochromatic Kr in it. Okay, so the goal is to show there exists a good coloring of Kn, and we show this by showing that the probability of there exists a good coloring Kn is bigger than 0. If you remember in the very first lecture, I told you that when we say probabilistic combinatorics, the general idea is that if you want to show the existence of a particular structure, it's enough to define an appropriate probability space and show that a randomly chosen element of this space with positive probability has the desired property. And that shows the existence of the structure that we want. So if I show that the probability of existence of a good coloring of Kn is positive, that means there exists a good coloring of Kn. Because the only way for probability to become positive is that at least one such structure exists. Okay, so when you want to show that a probability is bigger than 0, one equivalent way to do that is to show that the probability of complement of that event is less than 1. So equivalently, we show that probability that there does not exist a good coloring of Kn, which is same as probability that there exists a monochromatic Kr in Kn is less than 1. There does not exist a good coloring means there exists a monochromatic Kr, because good coloring, we said, we define it to be not the event that there does not exist a monochromatic Kr. Okay, so let's see how we can show this. So to do this, so probability that there exists a monochromatic Kr and Kn, we want to show that it's less than 1. So let's start with the left-hand side, probability that there exists a monochromatic Kr and Kn. So let's see what this event is. So when can I say that there exists a monochromatic Kr in Kn? So this means either, so see how many vertices do I have? I have n vertices, right? So one way to have monochromatic Kr is that, let's say the vertices 1 to R be blue, or vertices 1 to R be red. Okay, in those cases we will have a monochromatic Kr. So let's see if we write this, so let V, I can write after this. So probability that, let's say V1 to VR, so there is a Kn of this is red Kr, or Kn of V1 to VR is a blue Kr. Right, remember this is a notation for induced subgraph. So if I consider R vertices, let's say I want to have red Kr or blue Kr. So to have a monochromatic KR, how many ways, how many options do I have in order to have a monochromatic KR in Kn? One way to do it is to consider the first R vertices and have it red, have all the edges in red. Another way is to consider the first R vertices and connect all of them, each two of them, with blue edge. So in that case, I will have a blue KR. What else? What other option do I have in order to have a monochromatic KR in Kn? So another possibility I can say, I will have to consider R vertices, but it doesn't have to be the first R vertices. I can consider, for example, let's say V1, V3, V4, V. Okay, by the way, here we're talking about N and K in the notation of the theorem. So let me also use the book's notation, which is using K. K here. K, VK, VK. Okay, so another thing is that I can have V1, I can skip V2 and then go all the way to K plus 1, right? So this can be a red K, K or blue KK. So this can be a red KK or Kn of V1, V3, again, same thing, VK plus 1 is a blue KK. Okay, all the way to Kn of V1. Okay, my last option would be like the last K of them would be, again, all the edges between them to be all red or all blue. So I can have Kn of V n minus K plus 1 all the way to Vn, again, is red KK or Kn of V n minus K plus 1 to N is a blue KK. So here V equals V1 to Vn is the set of vertices. Okay, so probability of the event that there exists a monochromatic KK in Kn, we decomposed it into smaller events. So that means either this happens, or this happens, or this happens, all the way to this happens, or this happens. Okay. Now, I can, use a notation because it's very long right now, right? So I can use a notation to make it look nicer and more abbreviated. So now I can say let A1 to be the event that so what was the first one? Kn of V1 to Vk is a red KK. Okay, so we can write it in the event that Kn of V1 to A, red, K, K. So what is probability of A1? Probability of A1. So I want, okay, remember we have n vertices and it's Kn, so we have n choose two edges. Now we want anything between the first K vertices to be red. So what happens, so this is, like the first vertex, the first edge is red with probability 1/2. Second edge is red with probability 1/2 all the way to, so how many, so these are all red edges. How many 1/2 do I have? K choose 2 times. Okay. So I want, let me draw a picture for you here. See, this is, let's say, the first K of them. And then there are some other as well here. So I want any two edges in, this is, let's say, V1, V2. I have V6, V7, V8, V9, V10, V11. Okay, so I want any two edges here, any edge here between Vi and Vj, if I and j is less than 5. So Vi, Vj, or I and j less than equal to 5 is red. So each one happens, each of these edges is red with probability 1/2. So what is the probability that all these edges are red? Because each one is independent, each edge is independent of others. So the probability that the first edge is red is 1/2, second edge is red is 1/2, right? Third edge is 1/2. The probability that the third edge is red is 1/2, and so on. So see, so this one again, red, red. See, all of these are red. So how many do I have here? So 5 choose to such edge. So this is the probability that we have a K choose to such elements. So this is 1/2 to power K choose 2. Okay, remember the induced subgraph is a graph of size with K vertices, right? So I don't need to consider the rest because induced subgraph, I'm just dealing with this part, the left part. Now, even if you consider the right part, if you want to include the right part as well, still you get the same result because, well, we don't care about the rest of edges, right? So the rest of edges can be anything. So I just need to make sure that these happens. Well, for the rest, you can consider the rest to be all red or all blue or some part red, some part blue. So you can consider the probability for each of those graphs and then add the probabilities. You will see that again, you get the same number. Okay. So no matter whether I include the rest or no, technically I shouldn't include the rest because induced subgraph here has K vertices, but even if you can include them, you still get the same result. Okay. So here, this is basically the picture or figure. Let me write here that This is the figure for n equals, how much was it? 11, and my k is 5. Okay. So P of A1 is 1/2 to power k choose 2, and A1 was the event that Kn of this subset is a red Kk. So similarly, if I let B1 to be the event that Kn of V1 K blue Kk this time, then I can say that probability of B1 is equal to 2 times, probability of B1 is again similar argument. Instead of red, I have blue, 1/2 to power k choose 2. And again, similarly, I can talk about similarly define A2 and all the way to, so how many AIs do I have? Because remember, each AI corresponds to one subset of V1 to Vn with k elements. So how many subsets with k elements do I have from a set with n elements? Well, obviously, n choose k. So A2 all the way to A, n choose k, and define B2 all the way to B sub n choose k. And again, they have same probabilities, and P AI equals P and BI equals, again, same 1/2 to power k choose 2 for I, again, between 1 to k choose 2. So we're almost done. So again, remember how these AIs and BIs were involved in the game, because we wanted to find probability that of existence of monochromatic KK and KN. So that means probability of existence of a monochromatic KK and KN is equal to probability of A1 and union A2 union A sub n choose k union B1 union all the way to B sub n choose k. Now, this probability is less than or equal to P of A1 plus P of A2, P of A sub n choose k plus P of B1 plus all the way to P of B n choose k. If you remember, this was a property we mentioned last time, and this is called by property we saw last time. And this property is called union bound. Why is it called union bound? Because it gives a bound for probability of union of some events. It says that probability of union of some events is less than or equal to addition of the probabilities. It will be equal to addition. It will be equal to additional probabilities if the events are mutually exclusive or pairwise disjoint, basically. Otherwise, it's going to be less. So in general, it's less than or equal. And we know that each of, okay, so let's simplify this. So I can make this one a little bit smaller here. Okay. And then this one is equal to, what was P of AI and P of BI? Each of them was 1/2 to power k choose 2. So 1/2 to power k choose 2 plus 1/2 the power k choose 2 k choose 2, then plus 1/2 the power k choose 2. So the first line is for AIs and second line for BIs. K choose 2, 1/2 the power k choose 2. So how many such elements do we have? Well, we have n choose k AIs and again n choose k BIs. So 2 times n choose k, 1/2 the power k choose 2. And this is n choose k, 2 to the power 1 minus k choose 2. 1/2 the power k choose 2 means 2 to the power minus k choose 2. So times 2 is 2 to the power 1 minus k choose 2. Now, again, this is exactly the expression we had in the assumption. Okay, let me show you the assumption again. See what was the assumption? If this expression is less than 1, so there you are. So my assumption this expression is less than 1. So this means that probability that there exists a monochromatic KK and KN less than 1. That means probability that we have good coloring n is bigger than 0. And finally, we can conclude that P or sorry, capital R of K and K is bigger than N as desired. Okay, so finally, remember our goal was to derive a lower bound for Ramsey numbers, and finally we are there. So corollary is that capital R of K and K is bigger than 2 to the power K over 2 for K bigger than or equal to 3. Okay, so let's see how we can prove this. Proof, let n be equal to floor of 2 to the power k over 2. So my claim is that it's enough to check that n choose k, 2 to the power 1 minus k choose 2 is less than 1. Why is it enough to check this? Since this would imply okay, once I check this, then the theorem that we just proved implies that capital R of K and K is bigger than N. Now, capital R of K and K bigger than N, remember capital R is integer itself, so if it's bigger than N, that means it has to be bigger than equal to bigger than or equal to N plus 1, which is floor 2 to the power K over 2 plus 1. Now, floor of a number plus 1 is always bigger than the number itself, right? You can easily check this. So this is bigger than 2 to the power k over 2 because floor of t plus 1 is bigger than t itself. Okay, so now to check. So it's left, we show that once we check this, we are done. So it just remains to check this. Now to check n choose k, 2 to the power 1 minus k, k choose 2 is less than 1. How can we check this? So n choose k times 2 to the power 1 minus k choose 2. Okay, so let's simplify this. This is less than equal to n to power k over k factorial times 2 to the power 1 minus k choose 2. And why is this true? Because n choose k is n factorial over k factorial times n minus k factorial. Now this one can be written as n times n minus 1 times n minus k plus 1 over k factorial, and this is less than or equal to n times n times n over k factorial, which is n to power k over k factorial. Okay, so it's a very simple justification for this inequality. And then this one is less than or equal to, well, n is floor of 2 to the power k over 2. So we can say that it's less than or equal to 2 to the power k over 2. And then to power k is going to be 2 to the power k over 2 to power k divided by k factorial times 2 to the power 1 minus k choose 2. Now this is 2 to the power k squared over 2 over k factorial. 2 to the power 1 minus k choose 2 means k times k minus 1 over 2. And if we simplify this, k squared over 2 and minus k squared over 2, they cancel. So it's going to be 2 to the power 1 plus k over 2 divided by k factorial. Now, if I call this number bk, let's say, call it bk, then I can say that bk plus 1 over bk is how much? bk plus 1 over bk is 2 to the power 1 plus k plus 1 over 2 divided by k plus 1 factorial divided by 2 to the power 1 plus k over 2 divided by k factorial. And then this is 2 to the power 1/2 or root 2 divided by k plus 1. And this one is going to be less than 1 for k bigger than or equal to 1. So that means bk is decreasing, right? So bk is decreasing. So once it gets less than 1, for an integer, it will be always less than 1 because it's decreasing. It's decreasing, and note that b3 is 2 to the power 1 plus 3 over 2 divided by 3 factorial. And this one is 2 to the power 5 over 2 divided by 6. And this one is 4. So 2 to the power 5 over 2 divided by 6. And this is 4 root 2 divided by 6. So this is equal to 4 root 2 divided by 6 less than 1. You can easily check that this is less than 1, and therefore bk is less than 1 for k bigger than equal to 3 as desired. Okay, so this is the proof of this part. Okay, so what have we shown so far? So far we proved that the upper bound and lower bound for Ramsey numbers R, K, and K are exponential functions. What were they, do you remember? So 4 to the power K over root K and 2 to the power K over 2, respectively. So upper bound and lower bound are exponential. So that means Ramsey number behave like exponential, but the exact base of the Ramsey number, if such base exists, is still unknown. But the exact base for RKK, of course, if it exists, is still unknown. Okay, so yeah, the next topic is using the moments, first and second moments, expected values. But let me finish this session for here, and then next time we'll start using the moments to derive results using that method. Okay, thank you very much, and see you soon.